This is the lecture for Friday, October 19th. This is the lecture for 6.1, an introduction to chemical bonding. So just a quick refresher on what we learned last unit. We learned about the valence electrons for every single element on the periodic table. We learned that metals typically have 1 to 3 valence electrons. We know that metals tend to lose their electrons and form positive charges. We learned that nonmetals tend to have 5 to 7 valence electrons, and they tend to gain electrons to form a negative charge. So what we're going to be doing with this in this unit is we're going to learn, based off of these valence electrons, what kind of bonds get formed from this. So the first term I want you guys to write down is chemical bond. Chemical bond is a force that holds atoms together. So a quick little refresher, we learned last unit about the octet rule. The octet rule just states that every single element on the periodic table wants to become stable like the noble gases are. Most of the noble gases, minus helium, have 8 valence electrons around them. And the reason they are so stable is because they have completely filled outer energy level. So they have 8 valence electrons around them and it's completely filled. The reason why they're stable is because they have a lower potential energy than the rest of the elements. So in order to get this noble gas configuration, elements on the periodic table will gain or lose electrons to form ions and become isoelectronic to these noble gases, meaning they have the same number of valence electrons. So valence electrons, another quick refresher. This is literally just the electrons that are the furthest away from the nucleus. These are the ones that are involved in bonding, gained or lost. So just again, group 1 has 1 valence electron. Group 2, 2 valence electrons. Group 13 has 3. Group 14 has 4. Group 15, 5. 16 has 6 valence electrons. Group 17 has 7. And for the most part, group 18 has 8 valence electrons. And so what they're going to do is to get to these 8 valence electrons. They can either transfer, that we'll figure out which ones do that today, their valence electrons, or they can share their valence electrons. And what I mean by that are metals tend to lose their electrons, and they tend to lose them to nonmetals, which like to gain them. So they're actually going to transfer their electrons over, or sharing. Some electrons or atoms, they don't like to typically give away their electrons because maybe I have 2 nonmetals bonding together. Well, both of them like electrons. They're not just going to give their electrons over. So sometimes they'll share their electrons so they both can get to that octet to get 8 electrons around it. So the 3 types of bonds we'll be talking about today are called ionic, covalent, and metallic bonds. We'll go ahead and start with ionic bonds. Ionic bonds are bonds between metals and nonmetals. And you need to know this is a transfer of electrons. So if you're watching this video right now, make sure that you're writing everything in red on your notes as I'm going through this. So they're going to transfer electrons. These are going to be metals and nonmetals. So let's look at, for example, sodium, which is a metal, Na, which is a group 1 metal, which means it has 1 valence electron on it. So if I wanted to draw the Lewis dot structure, that's what it would look like. And let's say we're trying to get this to bond to chlorine. Chlorine is a nonmetal, and it has 7 valence electrons because it's in group 17. So first 2 on top, 3, 4, 5, 6, 7 electrons. So in an ionic bond, if I were going to take a metal and a nonmetal, and what would happen is sodium, because sodium wants to lose its 1 electron to get to the octet, it's going to lose this 1 electron by transferring it over to a nonmetal. And since chlorine wants to gain 1 electron, it's going to gain it from the metal. So this is that transfer, this loss or gain of electrons that's happening. And because sodium has lost that 1 electron, it gives it an overall positive 1 charge. And now that chlorine has gained one electron, now it has one more negative charge, so it's going to get a -1 charge. So I have now these charges on these ions. I have a positive and a negative that are attracted electrostatically. What you need to know, probably the most important thing about this, even though sodium has a +1 charge, and even though chlorine has a -1 charge on it now, once that electron has been transferred over, when I put these two together, it is electrically neutral. What that means is these charges cancel out. So a +1 and a -1 are going to cancel to make just NaCl. It has absolutely no charge on it, so it is a neutral. You know sodium chloride, obviously, as table salt. This is not the only type of salt there is. So all ionic bonds, every single one of them, anytime you put a metal to a nonmetal, they will all be considered a salt. So let's say I take magnesium and put it with chlorine, or if I take magnesium and put it with fluorine or anything like that. Since I have a metal and a nonmetal, that makes a salt. Not everything is going to have, not all salts have to be sodium chloride. The term that we use for all ionic compounds is called a formula unit. And the reason for that is because ionic compounds tend to make crystal structures. They tend to form these lattice structures in them. And so we use the term formula unit to show that that's the smallest number of ions that are in there. So just anytime you hear the words formula units, you need to think in your head, this is an ionic bond. This is going to be a metal to a nonmetal every single time. And this is just darn cute. The name's Bond, ionic bond, taken, not shared. I love Chemistry Cat. And here's another joke for you guys. If you guys just want to read, I'll give you a couple seconds. All right, so going back into this, what's happening, just to show this to you again, except this time we're going to do it with Bohr models. We're going to pretend that we have a Bohr model of an atom. And let's take the same thing. I'm going to take sodium and I'm going to take chlorine. So sodium, its electron configuration is 1s2, 2s2, 2p6, and 3s1. And so what I have here is 2 electrons in the first energy level. So let's go ahead and pull these down. And I have 8 electrons in the second energy level. And I have 1 electron in the third energy level. And of course, in the center is my nucleus with all my protons and neutrons. And then we're going to take chlorine over here, which has the electron configuration 1s2, 2s2, 2p6, 3s2, 3p5. And so pretty much the same thing. I have 2 electrons in the first energy level, 8 in the second, and I'm going to have 7 in my third energy level. And so what you have to remember, I have a metal to a nonmetal. It's going to be an ionic bond. So that means that you're going to be transferring over your electrons. 7. And so because of this, it's always going to transfer from the metal to the nonmetal every single time, because metals are going to lose their electrons and nonmetals will always gain those electrons. So 1, 2, 3, 4, 5, 6, 7. All right. So all that's happening, same thing, is I'm taking 1 electron from sodium, because sodium wants to get rid of this 1 electron, so it now has 8 electrons in its valence shell. So once it gets rid of this electron, so it's going to transfer this on over to chlorine, Now it's lost an electron. Now I make sodium with a +1 charge. And here, chlorine had 1, 2, 3, 4, 5, 6, 7 in its outer shell to begin with. It gained 1 electron, so now it has 8 valence electrons. It's now happy, and because it gained an electron, it gives it an overall -1 charge. And from that, I make NaCl. So the way that we draw these, every single time, we are going to draw them by first writing the elements. So I would write sodium with the dot on it. I'd write chlorine with its 7 dots around it, the Lewis dot diagrams. Then I would draw the transfer of the electron over. And that would be the electron transfer that you're going to see on your homework tonight. So this is how you draw electron transfer every single time. Then I'm going to ask you for the final combination, or the ion combination. So this will be that final combination that you see. And once sodium has lost its electron, now you have no more electrons around it. It gets a +1 charge. And then you have chlorine, which has now gained an electron and now has a -1 charge. So the final combination that I want you to write, I want you to put each one in brackets. So we're going to put sodium +1 in brackets. And then we're going to put chlorine with its 8 dots around it, because chlorine has gained an electron. You have to show that it's gained that electron. You're going to put that -1 charge also in brackets. And this would be my final combination that I would want to write. So make sure that you're putting them in brackets, and make sure all the valence electrons are around the nonmetal, because the nonmetal is the one gaining those electrons. So let's go ahead and do this for calcium and chlorine. This is going to be your example 2. So calcium, it's in group 2, so it has 2 valence electrons. So this would be its Lewis dot structure. And chlorine, as we just had, is group 17. It's going to have 7 valence electrons around it. Here we go. So chlorine only wants to gain 1 valence electron. And so what's going to happen is calcium is going to transfer over 1 of its electrons over to chlorine. So chlorine is now happy, but calcium still has 1 valence electron that it wants to get rid of. So what's going to happen is another chlorine atom with 7 valence electrons is going to come up, and it's going to take that extra electron that calcium had. So now calcium has lost both of its electrons, calcium's happy, and each chlorine now has 8 valence electrons around it, so they're happy. So the final combination, after you've drawn this electron transfer, is I have a calcium which has lost 2 valence electrons, so it now has a +2 charge. Put it in brackets. And now chlorine has 8 valence electrons around it. And because it's gained an electron, it has a -1 charge. Put that in brackets. And you have 2 of them. So you're going to put a 2 in the front to show that you have 2 chlorines for every 1 calcium ion that you have. So let's do this a couple more times. We have 3 examples. I'll go ahead and draw all of them out here. So potassium, okay. Group 1 has 1 valence electron, plus bromine has 7 valence electrons. So electron transfer, this 1 electron is going to transfer over to bromine, which only wants 1 electron, to make the final combination of potassium, lost an electron, it now has a +1 charge, and I have 1 bromine ion with 8 valence electrons now, and it gets a -1 charge. Aluminum and iodine. So aluminum is group 13, so it has 3 valence electrons. Iodine's group 17, so it's going to have 7 valence electrons. So iodine only wants one electron to fulfill the octet, so one electron from aluminum is going to transfer over to the nonmetal. Now, iodine's happy, but aluminum still has two valence electrons left over. So another iodine with 7 valence electrons comes up, and aluminum's going to transfer another electron over. So now I have 2 iodine ions that are completely happy. Aluminum still has 1 electron to get rid of, so another iodine is going to come up and take that last electron. So now all 4 are ions and they have fulfilled their octet. So I'm going to write metal first. It's lost 3 electrons, so I get a +3 charge. Put it in brackets. Then I'm going to write nonmetal next. Nonmetal has gained the electron, so now it has 8 valence electrons around it. And it gets a -1 charge. Put that in brackets, and I have 3 of them. So I'm going to put a 3 in front of the iodine. And then let's just do the last one. So nitrogen and magnesium. So nitrogen is in group 15, so it has 5 valence electrons. And then magnesium is in group 2. It has 2 valence electrons. So magnesium's the metal. It's going to be transferring the electrons over to the nonmetal nitrogen. So nitrogen wants 3 valence electrons, 3 more, to get to the octet. So magnesium's going to transfer 2 of its electrons over. So magnesium's happy, but nitrogen now has only 7 valence electrons. So it needs to get at least 1 more. So another magnesium's going to come up with 2 valence electrons. Nitrogen only needs 1 more to fulfill the octet. So nitrogen's now happy, but now magnesium has only 1 valence electron left over that it needs to get rid of. So another nitrogen with 5 valence electrons will be there to take that extra electron from magnesium. So now this magnesium's happy, but now I still need 2 more valence electrons for nitrogen to fulfill that octet. So I need yet another magnesium with 2 valence electrons, and nitrogen only needs 2 more. So after those 2 are transferred, every single one of these now has 8 valence electrons around it. So the final combination is going to be metal first. So magnesium comes first. Each magnesium has lost 2 electrons, so it's making a +2 charge. Put it in brackets. I have 3 magnesium, so I'm going to put a 3 in front of it. Then I'm going to write nonmetal second. The nonmetal has gained the electron, so I'm going to draw 8 dots around my nonmetal. And it has gained exactly 3 electrons, so it makes a -3 charge. Put this in brackets, and I have 2 nitrogens, and that's my final combination. So you will have to do this on your homework, and there will be questions like this on your test and quizzes. So make sure that you're practicing them, and just remember they have to fulfill the octet. That's why they're transferring those electrons every single time. All right, so properties. Again, make sure you're copying everything down in red into the blanks. But again, ionic bonds form because of a metal transferring its electrons over to a nonmetal. They're going to be solids, typically at room temperature, and they're going to have high melting points. So again, think of salt. Think sodium chloride every time you're doing this. If you put salt in a pan and you heat it, I don't think any of you have seen salt actually melt in front of your eyes. Most likely it's just going to burn. So they have very, very high melting points. They're very strong bonds. And if you dissolve salt in water, any type of salt, what's going to happen is it's going to break into its ions, and because now there's charges on them, it can actually conduct electricity. So it can conduct electricity when dissolved in water. So that's what this aqueous state means. It's just dissolved in water. Or it's molten state, meaning it's melted. It's now a liquid. It's not very volatile, meaning there's not a lot of salt particles or ionic compounds that are in the gaseous state, so it won't have a very high volatility. And again, as you know, you throw salt in water, it dissolves. All salts, most salts, will dissolve in water. So now let's talk about covalent bonds. Covalent is the sharing portion, and sharing means caring, so that's the easiest way to remember that. But it's always going to be when they share electrons. So this will always be between two nonmetals every single time. So for example, carbon has 4 valence electrons. So I'm just going to go ahead and draw the 4 on either side just to kind of prove this point. And let's say it wants to bond to hydrogen. Carbon wants 8 valence electrons around it. Hydrogen has 1 valence electron, but remember, when hydrogen forms an ion, it's going to be isoelectronic to helium, and helium only has 2 valence electrons. So hydrogen only wants 2 valence electrons. So if I take hydrogen and I go ahead and share this electron with carbon, let's say I put this one hydrogen here, I have an electron that comes from hydrogen, I put another one here, another one here, and another one here. Now I have 4 hydrogens and 1 carbon. What's happening here is the hydrogen and the carbon, they're not transferring their electrons over anymore. Now they're kind of sharing these electrons between the carbon and hydrogen atoms. And so because of this, I now have 1, 2, 3, 4, 5, 6, 7, 8 electrons that are surrounding carbon, so carbon feels like it's fulfilled its octet. And hydrogen, which only wants 2 valence electrons, has its 2 valence electrons around it. And so because of the sharing of these electrons, they fulfill their octet, or in the case of hydrogen, it's duplet. Just like in an ionic compound, it was called a formula unit. A covalent compound, the term for that is called a molecule. So you do need to know, if I ever on a test or a quiz say this is a molecule, first thing that needs to go off is this is a covalent bond. This is going to be a nonmetal to a nonmetal. So properties of covalent compounds. It's between a nonmetal and a nonmetal. They can be pretty much any state of matter. They can be solids, liquids, or gases. They have very low melting points. So an easy way to remember this is sugar. Sugar is a covalent compound because C6H12O6. They're all nonmetals. Carbon, hydrogen, oxygen, all nonmetals. Now sugar, it's really easy to melt sugar. You stick it in a pan, turn up the temperature just a little bit, and immediately melts and then starts to burn. They all have low melting points. They do not conduct electricity, even when dissolved in water. So if they dissolve in water, what happens is they stay together as one molecule. They're not going to break up into ions. And because they don't break up into ions, there's no way for electricity or to be conducted in there. They have a high volatility, and that's just because of their low melting points. Because they can melt, now you have more molecules in the gaseous state, and so it's a little bit more volatile. Metallic bonds are literally just metal-metal bonds. So metal to nonmetal is going to be ionic, nonmetal to nonmetal is going to be covalent, and then metal to metal is going to be your metallic bonds. And the best way to look at that is this is a sea of electrons. They're going to all pretty much share their electrons because these electrons are they're delocalized, which means that they don't belong to one atom anymore. They're kind of in an orbital that's shared by a bunch of different atoms. And so because of that, they kind of just swarm around a little bit, and they're transferred between atoms. So just remember the term sea of electrons whenever you're thinking metallic bonds. Properties of metallic bonds. You know these properties already. Metals do not dissolve in water. Metals have very high melting points. Metals conduct electricity. Metals have luster. They're shiny. You can bend them easily. They're malleable. You can pull them into wire. They're very ductile. You already know these properties. So metal-metal bonds have those properties of metals. So ionic versus covalent bonds. So not all bonds are going to be 100% ionic or 100% covalent. They're going to actually have properties of both ionic character and covalent character, just because depending on where you are on the periodic table, they can actually have a little bit more of a metal character, or maybe they're halfway between metal and non-metal. And the best way to determine this is by their electronegativities. So from last unit, we talked about trends of the periodic table, and electronegativity was one of them. Electronegativity just means how much does an atom like electrons? How much is it able to attract electrons to itself when it's in a bond? So if it likes electrons, it's going to have a higher electronegativity, and that would include your nonmetals, the ones that want to gain the electrons. And if they don't like electrons, like metals don't, they typically want to lose them, they're going to have a lower electronegativity. And based off of the difference in electronegativity, you can figure out if this bond is going to be more on the ionic side or if it's going to be more on the covalent side. And so let me go ahead and show you what this looks like here. There are three types of bonds that we're going to talk about. We already talked about ionic. This is metal to nonmetal. And what we're going to assume, if it's ionic, that means that electrons are literally getting transferred over. And it means that the electrons are unequally shared. It means one atom, the metal, is going to give away its electrons to the nonmetal. Now, there are two types of covalent bonds. You have nonpolar and you have polar. So if you want to think about it in terms of a magnet's going to have a north pole and a south pole. That the poles just mean that they're different. There's opposite charge, opposite sign, whatever it is. In this case, when we're talking about polar, we mean one side is going to have a positive end, one side's going to have a negative end. If it's nonpolar, that means there are no poles. You don't have a positive end, you don't have a negative end. So if it's polar covalent, that means it's a covalent bond, so they're still sharing their electrons, but one atom likes the electrons more than the other does. And so one atom's actually going to kind of steal the electrons a little bit and get them closer to them because they're more electronegative. They like those electrons. So this is an unequal sharing of electrons. One gets the electrons more than the other does. If it's a nonpolar covalent bond, that means they equally share those electrons. Neither atom wants the electrons more than the other does. So they're going to share them equally. So on this table, you do have the numbers that we give you. So you're going to be taking the electronegativity values and you're going to be subtracting them. And you're going to have three different ranges. If it's between 0 and 0.4, that means it's a nonpolar covalent bond, meaning, for instance, let's say I take carbon and I bond it to another carbon, and they're sharing these electrons. Well, they have the same electronegativity values. They both like electrons just as much as the other one, so these electrons are, in essence, going to be shared equally. They're going to be kind of in the middle. So this will be my nonpolar covalent region. If after subtracting the electronegativity values and it's between 1.67 and 0.4, that means that it's a polar covalent bond. They don't share them equally. So this case would be, for instance, HCl. Hydrogen tends to get rid of its electrons, so it's not very electronegative. It doesn't like electrons. Chlorine, on the other hand, loves to gain electrons. It's very electronegative. So if these two were sharing electrons, you would see these electrons closer to chlorine and further away from hydrogen because chlorine's pulling them towards itself. So this is what I mean by not shared equally. So they're still sharing those electrons to fulfill their octet, but chlorine, the electrons spend more time with chlorine than they're going to be spending with hydrogen. And then, of course, if you get in the range of 1.67 to 4, that means it's an ionic bond. That means you're transferring your electrons from metal to nonmetal. So this is just another example of this polar covalent bond versus nonpolar covalent bond. So here I have two carbons. They both have the same electronegativity value, so they're going to be sharing those electrons equally. You'll see them in between. If it is polar, these electrons are going to be spending way more time around the oxygen than they will around the hydrogen, and that's just because oxygen is more electronegative. It likes those electrons more, so it's going to attract them a little bit more than hydrogen will. And so it's going to be an unequal bond, an unequal sharing of those electrons. This table right here is every single electronegativity value you'll be using in doing homework, taking quizzes, and everything else. So on quizzes and tests, you will be given this table, so don't freak out that you have to memorize anything. You will be given this table, so don't worry about that. All you have to be able to do is use this table and know how to find those numbers and just subtract them to find that difference. So let's go ahead and do some practice. Let me move this first. There we go. So we're going to find what type of bond it is. So we see it's sodium, Na, which we know is a metal, and we have Cl, which is a nonmetal. And so just looking at it, metal to nonmetal, you're just going to assume, yes, it's an ionic bond. Please don't do that when you're doing these problems. Most likely, if you see a metal and a nonmetal together, it will be an ionic bond, but it's not necessarily always the case. And that's because sometimes one of them likes the electrons a little bit more than the other, so you have to make sure you're looking at those electronegativity values. So what we're going to do is we're going to find sodium on the periodic table here, which is a 0.9 value. So I'm going to put 0.9. And then I'm going to find chlorine, which is a 3.0. And all I'm going to do is just subtract them. So 3 minus 0.9 gives me 2.1. So now I'm going to look at this range back here. I know that if it is 2.1, that falls in the category of 1.67 to 4, so therefore, yes, I was correct. This will be an ionic bond. So this forms an ionic bond. And that's how you're going to be doing every single one of them. You will have to remember those numbers, so you need to know off the top of your head for quizzes and for tests that if it's between 0 and 0.4, this is going to be non-polar covalent. If it's between 0.4 and 1.67, you need to know that this is going to be polar covalent. And if it's between 1.67 and 4, this is going to be an ionic bond. So you definitely need to know those off the top of your head. So next one, sulfur and selenium. These are two nonmetals. And because of that, you know that it's most likely going to be covalent, but you don't know if it's going to be nonpolar or if it's going to be polar. So we're going to find sulfur on here. Sulfur is 2.5, and selenium is 2.6. So I'm going to go ahead and subtract the two. And that's going to give me 0.1. 0.1 tells me this is a nonpolar covalent bond. So because of that, it's going to share its electrons equally between the sulfur and the selenium. It's going to share them. So hydrogen and oxygen. Hydrogen is 2.1 and oxygen is 3.5. So go ahead and subtract the 2, and we get 1.4. So when we look at that, we're going to realize this is a polar covalent bond. This means that they do not share the electrons equally. Oxygen is more electronegative, so the electrons are going to spend more time hanging around oxygen. Lithium and iodine. Lithium is 1.0, and iodine is 2.7. So let's go ahead and subtract them out. And I'm going to get 1.7, which is actually in the ionic region, but very close to polar covalent. So this is an ionic bond. I have my metal lithium and my non-metal iodine. So when you're doing this, just make sure it doesn't matter which one you're subtracting from whichever other electronegativity value you're using, as long as you're just ending up with a positive number. So just make sure they subtract out to make a positive and not a negative number. So iron and chlorine, let's do this last one. Iron is 1.8, and chlorine is 3.0. So subtracting the 2, I'm going to get 1.2, and 1.2 is in the polar covalent region. So if you look at it, iron's a metal. Chlorine's a nonmetal. If you looked at that, you would say, oh no, that's an ionic bond. But in actuality, it doesn't act like an ionic bond. It acts more like a polar covalent bond. They're actually sharing those electrons a whole lot more than iron's transferring those electrons over to chlorine. So this is why you need to use those electronegativity values every time you're doing this. So this ends the lecture for 6.1. Just make sure if you are not in Miss Gaiman's class and watching this video, this is where you're going to go ahead and turn off the tape. So the homework assignment is going to be on the same sheet. Make sure you're doing every single problem and use those electronegativity values for that table in number 2. And go ahead and turn that in. If you're in Miss Gaiman's class, go ahead and keep watching. We're going to do an activity where you're going to be using these little puzzles here that I have to figure out how many cations and how many anions are going to bond together to form ionic bonds. So here is aluminum. Aluminum has, it's in group 13, it's going to have 3 valence electrons. So these 3 little triangles here are the valence electrons. And if you're looking at anything that has kind of inward portions, sulfur is in group 16. It has 6 valence electrons. It wants to gain 2 to get to 8. And so what I did here is you have 2 spots where you can fit in 2 valence electrons so it can fill its octet. So this is where you're just going to kind of fit them together. Really wish I could move this. All right, so let me draw them out. So if I were going to do an example, I think the first example on your activity sheet that you're going to be doing is aluminum and chlorine. I'm going to go ahead and do this for you so you kind of know what to do. You're going to take one of your aluminums, and you're just going to try to fit them together. So here's a chlorine. And you're going to notice chlorine just wants one single valence electron to fill the octet. And aluminum has 1, 2, 3 to give. And so this one chlorine is going to fit onto this one valence electron that aluminum's trying to get rid of. Now, once that happens, chlorine has filled its octet, but aluminum still has 2 more valence electrons to get rid of. So what's going to happen is another chlorine's going to come up, and it's going to take this 1 more valence electron that aluminum has. So aluminum is now given away 2, and chlorine I now have 2 chlorines that have filled octets. So aluminum still has 1 more to give, so another chlorine is going to come up and it's going to go ahead and take this last valence electron. So when you're done with this, it should look like this. To show that they fit together. And once they fit together, you can realize that now that aluminum is given 3 of them, it's take 1 aluminum for every 3 chlorines to make an ionic bond for all of them. So that's how you're going to do every single one of them. Make sure that they all fit together. And once they fit together, figure out how many of the metals are going to bond to how many of the nonmetals so that it can form a formula unit. If you can do this without these little puzzle pieces, I say go for it. But if you need these puzzle pieces to kind of help you see how many valence electrons it needs or how many valence electrons it wants to gain to get to the octet, please use those. So the rest of class, just make sure you're fitting these together using these puzzles. You're going to go ahead and pair up into 2s to do this and figure out how they fit together. You have to make sure to turn in this sheet of paper before you leave class today. And then, of course, again, your homework is the backside of the notes. All right, this ends the lecture for today.